Alice, Bob, and Eve explain quantum gates.
You know, Bob, light switches are so simple objects. Flip the switch up, the light turns on. Flip it down, the light turns off.
That light switch is actually a great starting point for understanding quantum gates, which are the building blocks of quantum computing.
Quantum gates are exactly what we need to talk about. They're how we manipulate qubits to perform quantum computations.
How does my simple light switch relate to quantum gates?
Your light switch is like a classical logic gate. It has two possible states, on or off, which we can think of as 1 or 0. It performs a very simple operation.
But quantum gates are more like a dimmer switch. They don't just flip between on and off. They can create blends of states and even change how states relate to each other.
What kinds of quantum gates are there?
There are single qubit gates that act on just one qubit, like your switch affects just one light. The X gate is actually the quantum version of your light switch. It flips a ket 0 to ket 1 and vice versa.
Then there's the Hadamard gate, which is more like turning this dimmer to exactly half brightness. It takes a ket 0 or ket 1 and puts it in an equal superposition of both states.
What about gates that affect multiple qubits?
That's where it gets really interesting. The C0 gate, controlled not, is like having two light switches, where flipping the second switch depends on the position of the first switch.
Imagine you have not one but two of those dimmer switches. Further imagine the first switch controls whether the second switch works. If the first switch is on, then the second switch flips. If the first switch is off, then the second switch doesn't change.
These gates sound like they have specific purposes.
They do. Just like different kitchen tools perform different tasks, quantum gates perform specific operations. The Z gate changes the phase of a qubit. It's like adjusting the timing of when your light blinks rather than its brightness.
Rotation gates like Rx, Ry, and Rz rotate qubits around different axes of what we call the block sphere, changing the probability and phase in specific ways.
How many quantum gates do we need to build a quantum computer?
Surprisingly few. With just a small set of gates, like the Hadamard, C0, and T gates, we can approximate any quantum operation to arbitrary precision. This is called a universal gate set.
It's like how with just a few types of Lego bricks, you can build incredibly complex structures. Quantum algorithms are sequences of these gates applied in specific orders.
So my simple on-off switch is like the classical cousin of quantum gates, which can not only turn things on and off, but also create blends of on and off, adjust timing, and even connect operations between different qubits?
Exactly. And the art of quantum programming is figuring out which sequence of these gates will transform your input qubits into output qubits that contain the answer to your problem.
All of quantum computing, from Shor's algorithm to quantum simulation, is built from these fundamental operations, just like how complex electrical systems start with simple switches and circuits.